Hey everyone, welcome to Insights by Arish. Today we are going to implement iris flower classification project. This is a very basic project in machine learning domain. Every beginner starts with this particular project. Now beginning with, the iris flower classification dataset can be downloaded from the online sources like Kaggle as well as this dataset is also stored in an inbuilt mode in various libraries like Seaborn, sklearn, and we are going to import the dataset of iris flower from the sklearn library itself. We aren't going to download the dataset from any online source. So starting with, we will import pandas as PD, and then the library that we require to download the dataset from is sklearn. So we will say from sklearn.datasets you will import load iris. So here you have multiple datasets available in the sklearn library. From that we are going to load the iris dataset. Let's run this. Next thing that we want to do, we will load that iris dataset into some particular variable. So let's just say that the variable is iris, into which we will say load iris. If we would have downloaded this dataset from any online source like Kaggle, in that case we could have directly loaded that dataset into a data frame and we could have directly able to display that. But here, as we have loaded the dataset from the sklearn, we need to create the data frame out of that. So first we need to check what are the contents present in this load iris dataset. So to check the contents into that iris dataset, we will say dir of iris. Iris is a variable into which we have loaded our dataset. So let us check. So the dataset consists of data module, feature names, which are the column names that we have, and the target and target names. Now out of this contents, we need to create our data frame. And to create our data frame, let us say that we'll say x is equal to pd dot data frame. Now here first we want the data to be loaded into this data frame. So we will say the dataset into which we have loaded it is the variable iris, and so we'll say iris dot data. Data is present in the iris dataset. And then we also need to name that columns. If we don't provide any column names, then it will assume some dummy values there. So we'll say columns is equal to, now in the columns, on the columns place, you have a content here known as feature names. You need to provide that feature names element to here as a column names, and it will just extract the column name for every column automatically. So we'll say iris dot feature names. Let us run this and let us try to display the first 5 rows of the dataset X. So as you can see, here we have got our dataset. In the iris dataset, you have 4 columns: sepal length, sepal width, petal length, and petal width, which are in the centimeter. And based upon this, you want to identify that, you want to classify that the flower belongs to which particular species. You have 3 particular species here: Setosa, versicolor, and virginica, and based upon all these parameters like sepal length, sepal width, petal length, and petal width, you want to identify the particular flower belongs to which species. So now here we have only input data frame. We don't have that category, we don't have that labeled values there which are stored in the target. So we will create another data frame for that. We'll say y is equal to pd dot data frame, and here we'll say we want the data as target. The target is the content present in the iris dataset. Now here we don't need to extract the column names from the iris dataset. We can just say any target name that we want here. So we'll say columns is equal to, I want the column name to be species. Let's run this, and this is iris. Let us try to display the first 5 rows of the dataset. As you can see, these are your species. If you want, you can just check for the unique values. So you can say y dot species dot unique. You have got 0, 1, 2. If you want to be more specific, you can replace these values with the original species name of Setosa, versicolor, and virginica. And to do so, we'll say y dot species dot replace. We are going to replace 0 with Setosa, 1 with versicolor, and 2 with virginica. And we will say in place is equal to true to make the changes permanent. Now again we will try to display the unique names from the species column of the Y data frame, and you can see now on the place of 0 you have Setosa, on the place of 1 you have versicolor, and on the place of 2 you have virginica. So we have just made the target values more specific in order to convert them into more readable format. Now the next thing that we can do here, if you want to perform an exploratory data analysis EDA on this particular data set, then in that case you need to actually concatenate this both the data sets, because the species, that is the target variable, the target column is present in a different data frame, while the X column, the input columns, are present in a different data frame. So let us assume that we want to perform any EDA here. So in that case we will concatenate it to a variable df. So in the df we will store the concatenated data frames. So we will say pd.concat, and the data frames that we want to concat here are, the first is X and the second is Y. And we also need to provide axis is equal to 1, because we are concatenating them on the basis of column wise and not row wise. So let us run this and let us try to display the first 5 rows of the df, and you can see now we have concatenated the input features and the target variable here. Now what kind of EDA we can perform here? We can see that what's the approximate, or you can say the average sepal length in this particular data frame, or the sepal width. So you can do something like this. You can just say I will import the library here of Seaborn. First import matplotlib.pyplot as plt, and then import Seaborn as SNS. Let's run this, and I can say here sns.distplot. This plot basically stands for distribution plot. It consists of your histogram, it consists of your KD plot, a kernel density estimation, and also the RUC plot. So you can just say true or false for whatever attributes you want to include, or the whatever attributes you want to exclude. So in this plot I want to check the distribution of sepal length. Let's say sepal length. So I will say def, and I will provide the column name from here. And let's run this. As you can see, this is the distribution that we have. If you want to remove these warnings are none of our business. So if you want to do so, we can say something like this here: import warnings dot filter warnings ignore. Let's run this, and now when you rerun this particular cell, you can see now we don't have that warning here. So this is the distribution. The blue line that you're able to see is your KD plot, that is a kernel density estimation. If you don't want that, you can say something like this: KD is equal to false. Now you don't have that, but in general you require that plot to be more specific. So here, as you can see, mostly the sepal length belongs to 5 to 7 centimeter. So majority of the sepal length in this particular data set, for every category of course, are between 5 to 7 centimeter. You can do the same particular analysis on different columns as well. If you want to check for the petal width, let's say you want to check for the petal width, you can say something like this here. You can just replace the column name, and this is the petal average petal width. So you can see here majority of the petal width is around 0.5 or between 1 to 2.5. So this all exploratory data analysis you can do from this particular data set. If you want to also check which particular category is a majority is present in majority in this particular data set, you can also plot the bar plot here. So you can say sns.barplot, and I will pass the species name here. Let's run this, and you can see in this particular data set, virginica is the species that is present in majority, followed by versicolor, and then there is Setosa. We have very few instances for the Setosa. Now that we have performed some exploratory data analysis, we need to check if it consists of any null values. Of course, it won't consist of any null values as it's an inbuilt data set from the library. but still we will confirm. We'll say df.isInit.sum. It doesn't consist of any null values, so we can directly start with the further process. Now that we have done everything, the next thing we have to do is, by taking the look at dataset, we can say we need to scale the dataset. The values are between any range, and we need to bring them onto one common scale. So we will use min-max scaling for this particular, and we won't include the data frame df anymore. We will just make our pre-processing on the data frame x. That's what we are going to utilize for as our input features. So we will say, let us first display it, and we need to scale this data. So to scale, we will import from sklearn.preprocessing. We will import min-max scaler, and then we will create a variable, or you can say the object of min-max scaler, which is a scaler is equal to min-max scaler. This is the object. Now we will actually perform the fit transform method on this data set. So we'll say x is equal to scaler dot fit transform, and will provide the x data set. The reason behind including this square brackets and colon is, if you don't provide this, it will store all the values, the transformed values, in the form of array and not in the form of data frame. And to store the values in the form of data frame, we have just provided that square bracket and colon. So let's run this, and let us again display the first 5 rows. Now you can see the data is scaled between 0 to 1, which means we have successfully performed the min-max scaling on this particular data set. The next thing that we want to do is, now that we are done with scaling, we don't have any categorical values here, we can go ahead with train test split. So we can say, or before going to train test split, one thing you can do here, we will just perform dimensionality reduction on this particular data set. We don't want all these dimensions. We just want to extract the important values from this particular data set, which are important for our model to learn. So we will perform principal component analysis technique, PCA, onto this particular data set. So we will say, from sklearn dot decomposition, you will import PCA, and you will create an object of PCA as a small PCA and PCA. You need to provide the value that how many important components you want to extract. You can provide it in 2 ways. Either you can say n components is equal to 2. In this case, it will only extract 2 important columns from the entire data set. But if you don't want to do something like this, if you want to in general extract the important data from the data set, you can just provide with the amount %. So let's say 0.95, that is, I want to extract 95% of important data from this particular data set, and we will store that in the xPCA. So xPCA is equal to PCA dot fit transform x. Let's run this, and let us try to say xPCA dot head. Okay. This is the xPCA which you have just performed fit. You can do something like this. You can, instead of performing just the fit method, you can say fit transform. Let's run this, and let us try to display the data. Now the data is not in the form of data frame, but that will do. It won't, because the head method won't work here, as there is no data frame. If you just try to check the first 10 values here from the xPCA, you can see these are your values. The values are in the format of 2 columns. You can also create a data frame out of that. You can just say x is equal to pd dot data frame, and you can pass your xPCA here, and you can say columns is equal to PC1, that is the principal component 1, and PC2, that is the principal component 2. And if you try to display your data set x head, now it will work. You can see you have 2 categories here now, principal component 1 and principal component 2. You can see initially we had 4 columns, but now we just have 2 columns. This is because we extracted only the important data from the columns. these are not the specifically extracted columns. We haven't extracted any specific column like just the sepal length or just the petal length. No, we have extracted the important values which are combined and stored into this two columns, principal component 1 and principal component 2. If you want, you can extract 98% of important data. So let's say 0.98, and now we will check how many columns we have. So we can create the new columns according to that. XPCA and the first 10 values. Now again you have just two columns. If you make it 99% of important data, you can see you still have two columns. That's fine. Let me rerun this. So now we will pass this particular data set to our train test split. So we will perform train test split here. So from sklearn dot model selection, we will import train test split, and here we will say xtrain comma xtest comma ytrain and ytest, and we will say train test split. You will pass this x data frame. This is the new x data frame, not the original one with 4 columns. This is how you do dimensionality reduction in case when you have a lot of dimensions and that makes the learning process slow for your model. So x comma y into which we have stored our target, and we'll say test size is equal to 0.2, random state is equal to 42. Let's run this and let us try to check how many data we have in our training and testing set. So xtrain.shape and xtest.shape. So we have 120 rows in training set and 30 rows in testing set. Now that we have performed train test split, next we want to choose which particular classification algorithm is better to work upon. To choose, you can just randomly say that whatever algorithm you want, like naive Bayes, support vector machine, logistic regression, anything you can choose. But if you want to be more technical, you just implement the K4 cross validation in order to select or choose the best algorithm for this to build the model upon. So to do that, we will import cross validation score, and we'll say from sklearn dot model selection, you will import cross val score, and you will create a function here, and whatever algorithms you want to test, you can just import them randomly. So you can say from sklearn dot linear model, just a minute, you will import logistic regression. Then from sklearn dot ensemble, you will import random forest classifier. Then from sklearn dot naive Bayes, you can import multinomial naive Bayes, and from sklearn dot support vector machine SVM, you can import support vector classifier. You want to test this particular classification algorithms, that is which one is the best to use. So you will use the cross validation score now. So let us create a function in order to, instead of writing the code again and again, so we'll say def kfold, and we'll pass our estimator. Estimator is basically the algorithm onto which we want to estimate. So estimator, then the input, which will be our training set or either the testing set, xtest or xtrain, and then the target, which will be either the ytest or ytrain. And then into this we'll say return the cross validation score of estimator, input and target. And in general, it will create n number of cross validations here, and it will return us the score for every validation. As you can see here, let us try. So we can call the function kfold, and here we'll pass our first estimator, which is logistic regression, with the parenthesis, then the input that we want here, which is our xtrain, and the output is ytrain. Let us run this. As you can see, it has performed 5 cross validations here. It has performed k folds here, and it has returned us the accuracy for every fold. What you can do here, you can just say here mean, which means it will just take the mean of all the accuracies and will return us the approximate average accuracy here. So let's run this, and we can multiply it by 100 if you want it in percent. So 86% accuracy is we will get 86% accuracy when we will use logistic regression. Let us try with other algorithms as well. So we can say next thing you can try is random forest classifier. Let's run this, and you are getting 94% accuracy when you are using random forest classifier. Let us try with k-fold cross validation on support vector machines, so SVC, and let's run this. So you are getting 95% accuracy when you are using support vector classifier, that is the support vector machines. So from this you can say that the best algorithm to use here is your support vector classifier. So we'll go ahead by using the this particular algorithm. So we'll say from now that we have already imported that, we will just directly start building our model. So we'll say model is equal to SVC. Now if you want to check what are hyperparameters here we have in SVC, you can just visit on Google and you can write support vector machines. You can check the official documentation of scikit-learn for support vector machines, and you can see here we have some hyperparameters like the value of C, the kernel which is RBF, the degree. So these are all the values that you have. If you want to check what's the appropriate value of C, the kernel is RBF, which will stay constant. If we don't change it to other kernels, we have some different kernels like liblinear also, but we'll keep it RBF here. Now we need to provide a value of C here, and if you want to check what is the best value of C in this particular case, you can just, before building the model, you will perform grid search CV here. By using the grid search CV, we evaluate that what are the best parameters, what are the best hyperparameters for our algorithm. So we can say from sklearn dot model selection import grid search CV, and here we will build a classifier. We'll say classifier is equal to grid search CV, and then whatever algorithm you want to work upon, here we are working upon SVC, so we'll pass that. And the next thing is, now we will supply a list of values for hyperparameters, and it will give us what hyperparameter is best and what particular hyperparameter will give us the best accuracy. So the hyperparameter in this case, as you can see here, is a C, which is the regularization parameter, and C, you can also see that it must be strictly positive, so you cannot give any negative value here. We'll go back to that and we'll say C is equal to, you can give multiple values of C, so I will start with 1, or you can start with 0.5, 1, 2 and 3, and then we'll say CLF, it is our classifier, dot fit on X train and on Y train. So next thing that we will do here, we will create a data frame here. So we will say CLF is equal to pd.dataframe, and here we will store CLF dot the CV underscore results underscore, and we will check the column names from this classifier. So these are all the columns, and we just want to check the parameter C and the mean test score for every parameter. So we can say something like this, that is from the classifier df, we just want to check parameter C and the mean test score. And we also sort the values depending upon the higher accuracy. Initial we will store the values with higher accuracy and then the instances with lower. So we want the mean test score to be showed in the descending manner. We'll say by mean test score, and ascending is equal to false. Let's run this. We have got some error here, parameter C and mean test score. So the issue here is we need to provide two brackets here, as we are just trying to display the data frame. You can see the best accuracy you are getting after using the parameter C as 0.5. When you supplied all the values for hyperparameters, it gave you after using what parameter you will get the best accuracy. And as we are trying to display the main test score in the ascending value, you will get the higher accuracy on the top. So you're getting basically the higher accuracy after using the parameter C as 0.5, and hence we will provide it C is equal to 0.5. And then we will say model.fit X train and Y train. Now that we have fitted our model, we can evaluate it. We can say model.score. On X test, we will evaluate our model on the testing set. So X test and Y test into 100. So you are getting 96% accuracy. Let us try to make some predictions here. So we'll say model.predict for X test. These are all your predictions. We'll store all these predictions in a variable called pred, and let us check the first 5 true labels. So the first 5 true labels are setosa, all setosa. So let us check some different. The true labels between 10 to 15, it's again same. Between 100 to 105, they are all Virginica. Okay, so let us check what our model has predicted for this. So we'll say pred from 100 to 105. Actually, we want to check the true labels from the testing set, and we don't have testing set is only consist of 30 rows. So hence we'll check for the first 5. The first 5 true labels are versicolor, setosa, virginica, and again versicolor twice. So let us check what our model has predicted for the first 5 instances. So for versicolor, it's versicolor. For setosa, again setosa. So the predictions are just accurate. The true labels and the predictions for the first 5 instances match completely, which means we have predicted the things very well. And as the accuracy is 96%, we expect that the predictions to be in that way. From sklearn.metrics, you import classification report and confusion matrix, and we will print the classification report consisting of true labels which are stored in Y test and the predicted labels which are stored in pred variable. As you can see, you are getting a precision of 100% for the category setosa and versicolor, and 92% precision for virginica, which is quite good. And again, the F1 score is very similar and good for every category, which means there is no imbalance of data set. Now that we have printed the classification report, the last thing we will do here, we will just display the confusion matrix using the C1 heat map. So we'll say sns.heatmap, and first we need to create the confusion matrix. So we'll say CF is equal to confusion matrix. We'll pass the true label which is stored in Y test and the pred, which is the predicted one, and we'll say normalize is equal to true, which means we want the values to be displayed in a percentage format. We'll pass that CF variable here. We'll say A0 is equal to true, which means we want to display the values on the grid. And the C map, the color of heat map that you want, I will provide it with a theme of crest. Let's run this. This is our confusion matrix, and as you can see, just take a look at diagonal values, which are basically for correct predictions. So the 100% prediction for the first class and for the third class, which is the setosa and virginica, and 89% for class versicolor. On the x-axis, we'll just plot the labels here. On the x-axis, we have predicted values. we have predicted values, and on the y-axis we have true values, that is the actual ones. So actual, let's display that. You can see on the x-axis you have predicted values, and on the y-axis you have actual values. So when you try, you can see only 11% times it's happening that the actual class is 1, that is the actual class is versicolor, but your model is predicting that flower to be from the Virginica category. But for every other flower, you can see that's 100% accuracy, that is the model is correctly classifying the flowers. So that was the confusion matrix, and this particular model that we built gives an accuracy of 96%. So that's the project for iris flower classification. That's it for the video. Thanks for watching.